Experiments in Physics with Dr. Frank Oppenheimer. A brief demonstration of the equipment used in the Library of Experiments in Physics, produced in cooperation with University of Colorado Television. Today's experiment.
In this experiment, one can study angular acceleration and the effects of moment of inertia by watching various wheels roll along an axle down an inclined plane of rails. The apparatus consists of two rails. One can see them a little better here, perhaps, and then two rulers mounted alongside of them, along which one can measure distance. The apparatus can also be tipped, and there's a little device at the end with several notches in it with sort of predetermined angles. If one measures the height above the level position and the length, then one can find out what the angle is. The first thing to do, of course, would be to get the apparatus level, both crossways so that there's no wandering one side or the other, and also very accurately level along this way. Of course, turn the level over to make sure that the level itself is performing properly. Having gotten that level in the lowest notch and making sure that the tracks are good and clean and using, if necessary, crocus cloth to get any dents or rust off them, one can then start the experiment. Perhaps the first thing to observe is the effect on the angle turned as a function of time. For that, it's perhaps most useful to use this largest diameter disc. One can set that on there, and of course, if it's level to start with, it won't roll downhill, but still the disc might not be quite balanced. It is, as you see, fairly well balanced here. It doesn't move. It should sit in any place you want, and one can balance it. And to illustrate the effect of the balancing, here's a length of tape, and one can see how large the effect of that tape is at putting an initial unbalance in, so that one can check these various wheels and rebalance them if they're not quite balanced with little bits of tape and even something heavier if you need it. Having done that, one can then set this up at some known angle. Let's take the smallest notch first and set this. If I set the tape even with the rails, then and let it go, then it'll roll down. Now it's gone to an angle of pi, and there was an angle of pi over 2, and I can see how long it takes to do that. For example, I'll start it here. I'll start the watch when I release it. And stop the watch when it hits an angle of pi. Similarly, I can do that again for starting it at 0 and seeing how long it takes to reach an angle of 2 pi. And do this for several times for each angle and up to 5 or 6 pi. Of course, when it gets rolling too fast, it may be hard to coordinate the time with the stopwatch. So that one can then test the relationship between the total angle turn as a function of time for a constant acceleration, and one can even calculate what the acceleration must have been approximately from the angle and the torque exerted because of that small axle. In addition to the study of the angle turned as a function of time, one can also study the effect of moment of inertia. There are several different shaped wheels here, cylinders, and here's one with the cylinder which is hollow. It's cut out. Here's the steel cylinder, and they're aluminum, and they're square blocks. One can actually look at these qualitatively first. One can run races with them. Let me just put that on there and release them both simultaneously and watch what happens. And clearly, the separation between them is increasing, so that one is being accelerated more rapidly than the other, and this does depend on the moment of inertia. Since moment of inertia affects the time that goes down there, one can use that time to measure the moment of inertia. One can start this at some point on here, let's say at 20 centimeters, with making sure that it's well centered and the rod is perpendicular to the rails, and then start a watch when it starts, and seeing how long it takes to get to some other point, and from that calculate the moment of inertia. However, since right at the start, any small irregularities or any slight unbalance in the wheel will have a larger effect, it's usually more accurate to allow it to start, say start at 20 centimeters, but start the watch only after it's gone a certain distance, take 9 centimeters since it's the easiest to take the square root of. I'll let it go. Now I'll start the watch when it's gone 9 centimeters and stop the watch when, let's say, it's gone 49 centimeters, or when it reaches 69 on here. And in that way, I can see, take that length of time over this interval, and from those two, from that time, I can calculate what the moment of inertia of this object must be. I can do it for a variety of things. You can even have some made up and that turn on axles, but they have to be symmetric in order to do this particular experiment. One can do that several times to see how reliable it is. One can do it for several angles. If you want to, you can even have it very steep, but then the measurements become very difficult. That's all, that's really all that's involved in performing this experiment.
Experiments in Physics with Dr. Frank Oppenheimer was produced in cooperation with University of Colorado Television.